Okay, so this is kind of a big theorem. It's called the fundamental theorem of algebra. Now, when something has this name, fundamental theorem, you know it's going to be kind of a big deal. And in fact, this theorem is where we've been going with pretty much everything that we've said about polynomials so far. The big idea is that polynomials are just like numbers. And just like numbers, we can factor them an awful lot. This theorem says that if we have any polynomial and pay attention to its degree is n, we can come up with a list of n complex numbers and use them to factor our polynomial as a product of linear factors, maybe with complex coefficients. So it might not look like x minus 3, but we can always get linear factors. And of course, every linear factor has a root that goes with it. We don't have the tools to prove this theorem yet. We need kind of the big guns of calculus in order to actually prove this theorem. It's not that easy. What we can do is interpret and apply this theorem. So what does this say? First of all, it says that if we have a polynomial with degree n, then it has exactly n roots. Degree 5, 5 roots. Degree 7, 7 roots. And then the way we phrase this comment is up to multiplicity. What that means is, if a root appears more than once, we count it more than once. If a root appears 7 times, we count it 7 times. The second thing that this tells us is that if we all know all of the roots and the leading coefficient, they uniquely determine the polynomial, is how we phrase it. What it means for those to uniquely determine the polynomial, it means there's one and only one polynomial that fits. So those exercises we did once we had the factor theorem, where we had a list of roots and a leading coefficient, the polynomial that we gave there was the only polynomial that had those roots and that leading coefficient. The last thing this tells us, and this is again something that we've been assuming for a long time, is that if we have a polynomial, it factors uniquely, just like numbers. So with numbers, we could, if we want to factor 30, we could start with 5 times 6 or 3 times 10. And either way, we'd end up with 5 times 2 times 3. We can start however we want. Same thing with polynomials. If we want to factor a polynomial, it doesn't matter what factor we start with. We'll end up with the same polynomials at the end. So this is really useful, and it kind of says that a lot of the assumptions that we were making as we worked with polynomials, those are actually true. Everything's going to work out fine. We're never going to encounter some sneaky polynomial that does something weird to us. One of the simple things we can do with this theorem is just look at a polynomial like this and say, okay, how many roots does it have? And all we have to do is look at it and say, what's the degree? This polynomial has degree 5, which means that without doing any extra math, we know right away that this has 5 roots. We can put that fact together with Descartes' rule of signs to make some really good guesses about how many of a polynomial's roots are going to be imaginary. So by imaginary, we mean a complex number that's not real. Suppose we wanted to analyze the roots of this polynomial. This polynomial has 1 sign change, so it has 1 positive real root. If we substitute negative x, remember that flips the sign of every term with an odd power of x. So 2x to the 6th stays there. Negative 7x to the 3rd becomes positive 7x to the 3rd. Negative x squared sits there, and then negative 4 sits there. This has 1 sign change, which means that the original polynomial has 1 negative real root. On the other hand, our polynomial has degree 6, so it has 6 roots total. It has 6 roots total. 1 of them is real and positive. 1 of them is real and negative. 0 is not a root because x is not a factor. So that means we have 4 imaginary roots. And we can know that. We can know that we're going to have 4 imaginary roots to this thing without doing any algebra at all, just by counting things, which is pretty neat.